Hi everyone, welcome back to my channel. As promised, this is the video where I explain the Anova table, and let's just get right into it. So again, these are the two variables that we were using the last time in my last two videos. The first one is the independent variable, it's called speed, and then we have the dependent variable, which is y, and it's called distance. And basically I put them in a data frame, I called it data, and then I fit the model. And we fit something called OLS, and this is actually, we got that from the stats model package from Python. And this basically fits an ordinary least squares regression model. Alright, and then we print out the model summary and the Anova results, or the Anova table. So let's look at the table. So I'm just gonna pick the things that are important for the sake of this video and which are relevant to simple linear regression, because we're only using one variable, one independent variable. But when we get into multiple linear regression, I'm gonna do another video where I explain all the different things that we have in the table that are for multiple linear regression. So let's look at what we have here. So again, here this is the dependent variable, so it's just telling you that y is the dependent variable. And here it specifies the model that we used. We said that we used the ordinary least squares model, and the method is least squares. Remember, this is what I explained in the previous videos when I was talking about minimizing the square distance from each point to the predicted point or to the line. This is just the date and time, not important. And then I'm just gonna go into r squared, because r squared is really important. So what is r squared? R squared is a percentage that explains the variance or the variability in y that is explained by the variability in x. So it says how much of the variability in the dependent variable, which is y, how much of this is explained by the variable x. And for this example, we have 65% or 0.65. Technically, it's not it's not a high number. It's not like this means that 65% of the variability in y is explained by x, but we obviously want this number to be bigger. How does the r squared help us in any way? First of all, if we fit another model and we get a higher r squared, this means that the other model is better. So I can use that to compare different models, but be careful, because technically if I add another variable to this model, so now the variable has only one x right here, but if I add another variable and I check the r squared is definitely going to increase. And if you want to know more about the r squared and its dynamics, then we can have another video about that, but just for the time of this video, this is the idea. So we want the r squared, we can use it to only look at different models with the same number of variables. So basically, if I take out this x and I put another x, so I put another variable, and I get the r squared, I'm gonna get a different r squared. And then I can compare the two r squareds together. And if the r squared from the new x is better, then this means that the other model is better. And because of this problem of, if we add more variables to the model, the r squared is gonna increase. That's why we use something called adjusted r squared. And basically the adjusted r squared is the same formula as the r squared, but we add a penalty to the r squared. So basically we penalize the model for adding more variables to the model, and we're going to explain this more in multiple linear regression, so just don't worry about it right now. So when we want to actually compare between models, using adjusted r squared is much better. Now, if we want to look at the f statistic, basically also penalizes the model for adding additional variables that are just noise and do not really contribute to the model. You can fit a model with one y and one x, and then try and add new variables to the model, so new x's to the model, or predictor variables, more predictor variables. And you will notice that the r squared is going to increase anyway. It's going to look better, but not that doesn't always mean that it's actually getting better, or it doesn't mean that the variables are actually important. And that's what the f-statistic helps us to do. And we're going to talk more about the f-statistic again in multiple linear regression. Also, AIC and BIC here are two things that we use to measure also, again, the error and how much we decrease the error by. But both of them have a penalty term that is added also to penalize for the extra variables. So I'm gonna scroll down and show you. So here are the two functions where we use the AIC and BIC. The AIC is the residual sum of squared, but we add 2d sigma squared, and the BIC we add log n of d sigma squared. And we can see that this penalty term that is added to the residual sum of squares penalizes the term if the number of variables increase. D here, not the letter D, means the number of variables, or the number of x variables, the number of predictors that we add to the model. So the more predictors we add to the model, the more that this whole thing is going to increase, and this is going to inflate the BIC, or inflate the residual sum of squares. And because, as we said, the residual sum of squares is anyway going to decrease when we add more variables to the model, but this penalty term here and here ensures that when we add these more terms, if they decrease the RSS, but they don't really decrease it by that much, then we're going to actually penalize the RSS so much by how much we increased the predictor variables. So they are really, really good measures of how important is this additional variables that we are adding to the model, and it will become more important actually when we go to multiple linear regression, which is not our case now. So the most important part actually here is this table, this really cute table. So again, from the table, we can look at the coefficients of the intercept and the x variable, and we can get the same exact linear equation that we got before. So we can say that y is equal to negative 17 plus 3.9x. Okay, now let's look at the x. So the coefficient, what does the coefficient mean? Here the coefficient means that keeping everything else constant, when I increase x by 1 unit, this is going to increase the y by 3.9 units. So the next thing that we want to look at is how actually important this coefficient is, like how important and significant this variable is to the model. How do we do that? Is by calculating something called the t-statistic. And basically, what we do is that, first of all, we calculate something called the standard error. The standard error is just how much the coefficient deviates from the real coefficient. So the standard error tells us the average amount that the estimate differs from the actual value, just exactly as the standard deviation, basically, same idea. So, and to calculate the t-statistic, we divide the coefficient by the standard error, and this gives us the t-statistic. So why do we need the t-statistic? Basically, the t-statistic measures the number of standard deviations that beta hat, or the coefficient, is away from 0. So basically, it's again the estimated coefficient divided by the standard error. And this answers the question of the null hypothesis of beta 1 equal to 0, and the alternative hypothesis that beta 1 is not equal to 0. So To answer this question, what does that mean? What does that mean that beta 1 is equal to 0 and beta 1? So when we say that our hypothesis is that beta 1 is equal to 0, this means that our hypothesis is that the coefficient that we got here is actually equal to 0. And this means if it's equal to 0, then it has no effect on y. This means that x is not significant. So this is the null hypothesis. So when we say beta 1 or beta, or called the coefficient, is equal to 0, this means that our hypothesis is that this coefficient or this x variable is not significant. And then alternative hypothesis is that we say, okay, the coefficient is actually not equal to 0, or beta or beta 1 or whatever is not equal to 0. And this means that in other words, the x variable, the predictor variable, the independent variable is actually significant. So to get to the answer, whether x is significant or not, or to accept or reject the null hypothesis, we look at something called the p-value. So what the p-value is basically the probability of observing any number equal to or larger than the modulus of t, assuming that the real beta 1 is actually equal to 0. So if we get the p-value here, anything that is below 0.05 is considered really small p-value, and when we see a really small p-value, we are confident enough to reject the null hypothesis. So we're confident to say that beta 1, or the coefficient of x, the actual coefficient of x, is actually not equal to 0, which means that x is a significant variable and we can add it to the model. And this is basically the idea of the t-statistic. That's it for our video. Thank you so much for watching. If you like the video, please give it a big thumbs up, and do make sure to check all the other videos on the channel. I'll see you later. Bye!